Hello and welcome to Algebra 2 Lesson 27. In this video, we're going to learn about solving systems of linear equations by elimination. So in the previous two lessons, we had a review of how to solve a system of linear equations in two variables, first by using the graphing method, and then second by using the substitution method. So if you've taken an Algebra 1 course in the past, again, none of this is new for you. You would have mastered all of these concepts before you got to this Algebra 2 course, but it's good to review it because in the next lesson, we're going to learn how to solve a system of linear equations in three variables. So it's good to have these refreshers before you start looking at some tougher material. Now, we already figured out that graphing was essentially just something we learned for conceptual purposes, right? We're not going to really use that. Substitution is a good method, and it's something we want to use when one of our variables has a coefficient of 1 or -1. For elimination, we want to use this when we have one pair of variable terms as opposites. So in other words, if I see something like -5x and 5x, or -10y and 10y, if I added those two together, they would sum to 0, right? -5x plus 5x is 0. Or -10y plus 10y is 0. So if I do that, that variable will become eliminated. Okay, and that's going to be the whole goal here. We're going to eliminate one of the variables from the system, so we have a linear equation of one variable that we can solve. Then we can plug back in to one of the original equations, and we can find the other one. All right, so solving linear systems in two variables with elimination. The very first thing you want to do is place both equations in standard form. Now, I know this definition of standard form, gets argued about and, oh, it's this and oh, it's that. For the purposes of this video and the purposes of making this very simple, let's just agree that standard form would be ax plus by equals c, where a, b, and c are just real numbers, and a and b are not both 0. Now, once we've done that, we want to transform one or possibly both of your equations in a way that one pair of variable terms are opposites, okay? Opposites. Remember the examples I gave. 5x and -5x, or 10y and -10y. So you want variable terms that are opposites. Now, on the easier problems, this is given to you. You start out that way. On the harder problems, you've got to transform one of the equations or you got to transform both of them, okay? And we'll see some examples of that. Now, once this is done, this is where your addition property of equality is going to come into play. You're going to add the left sides and set this equal to the sum of the right sides. And this will make more sense once we get into the example. All right, so once you've done your addition step, you will have eliminated one of the variables. So you're left with a linear equation in one variable. So you're going to solve the resulting equation. Okay, once that's done, you'll have x equals some value, or you might have y equals some value, depending on what went on. And then you're just going to find the other unknown using substitution. So whatever I find, I'm going to plug that back in for that particular variable in one of the original equations. I'm going to solve for the other unknown. Now, the last thing and the most important is to check the result. Remember, for you to have a solution for a system, it's got to work in both. Okay, it can't just work in one. So plug in for x and y in both. Let me highlight that, in both original equations. All right, so let's go ahead and get started with the first problem. So I have 3x minus y equals 5 and 4y equals 3x plus 7. So one thing I like to do, I like to number my equations just so I can refer to them. So let's say this is equation 1 and this is equation 2. So with equation 1, it already follows this format of ax plus by equals c. So we don't need to do anything there. With equation 2, not so much. But it's very simple to fix that. All I need to do is subtract 3x from both sides of the equation, and I would have -3x plus 4y is equal to 7. So now it matches this. And again, we're using the looser definition. So let me erase this real quick, and I will drag this up here and just say that we have 3x minus y equals 5, and then this guy, -3x plus 4y is equal to 7. So you can see why we put them both in standard form. It's easy to see the values that we have that are lined up on top of each other. I've got my 3x on top of negative 3x. I've got negative y on top of 4y. I've got 5 on top of 7. So everything's lined up. In this particular case, we have an easy example. I want you to notice that we have 3x and negative 3x. So we have a pair of variable terms that are opposites. So we don't need to do anything further other than proceed to the step where we add the left sides and set that equal to the sum of the right sides. Now, generally we do this vertically, but for the first one, I want to do it horizontally, just to show you something. If I start out with 3x minus y, and this is equal to 5, so everybody to this point would understand that it's okay to add 2 over here, as long as I add 2 over here. I added the same thing to both sides of the equation. But where people get confused is if I start doing stuff like this. Let's say I add this to this side. So I'm going to add the quantity negative 3x plus 4y. Based on what we've done so far in our algebra coursework, we would expect us to add the same exact thing over here. But what I'm going to do is I'm going to add 7 over here. Now, you might say, is that legal? Yes. I've added the same thing to both sides of the equation. It doesn't look the same, but I'm told because of this equal sign that they are the same. Negative 3x plus 4y is equal to 7, so it's the same as 7. So if I add this and this, I'm adding the same thing to both sides of an equation, and because of the addition property of equality, this is mathematically legal. Now, let's go ahead and add now and see what we get. So on the left, I would have 3x minus y. I'm just going to drop the parentheses here. So minus 3x plus 4y. And this equals 7 plus 5 is 12. Over here, we have that pair of variable terms. You have 3x and negative 3x. Those are going to cancel. And notice how when they cancel, the x variable is eliminated. Okay, it's gone. So I'm just left with a variable y. I have negative y plus 4y. That's going to give me 3y. And this is, of course, equal to 12. I can now solve my linear equation in one variable, divide both sides by 3. This will cancel. You'll get y is equal to 4. So once you've found that out, just erase everything. So again, y equals 4. So I would have, as an ordered pair, something, comma, 4. So because 4 is the solution for y in the system, that means it works here and here, okay, in equation 1 and 2. So I can use either equation to find x now. So let's go ahead and go with equation 1, because it seems easier. We have 3 times x minus, plug in a 4 for y, and this equals 5. So all I need to do is add 4 to each side of the equation. That's going to cancel. I'll have 3x is equal to, 5 plus 4 is 9. Let's go ahead and divide both sides of the equation by 3. And I'll get x is equal to 3. So as my ordered pair goes, it would be 3 for the x value, comma 4 for the y value. Now the last thing we want to do is make sure that we didn't make a mistake. Remember, this has to work in both equations to be a solution for the system. So I'm going to take 3 and multiply by x. X is 3. Subtract away 4, because 4 is y, and this should equal 5. 3 times 3 is 9. 9 minus 4 is 5. You get 5 equals 5. So it works out here. In the second equation, equation number 2, I would have 4 times y, y is 4, is equal to 3 times x, x is 3, plus 7. We know 4 times 4 is 16. 3 times 3 is 9. 9 plus 7 is 16 as well. So you get 16 equals 16, so it works out here as well. So our solution here is the ordered pair 3, comma 4. We're getting an x value of 3, a y value of 4. All right, so let's look at one that's a little bit more challenging. So we have negative 5x minus 6y equals 13. Negative 7 plus x equals negative 6y. Again, I like to number my equations just so I can refer to them. This is equation 1. This is going to be equation 2. Now, I want them each in standard form. So let me write this again. It's ax plus by equals c. So this one fits the bill. That's okay. This one, not so much. What I'd need to do is subtract x away from each side of the equation. So I would have negative 7 is equal to negative x minus 6y. And of course, I can just flip these around and write negative x minus 6y is equal to negative 7. So it matches this. And then let me erase all this. The other guy, equation 1, is negative 5x minus 6y is equal to 13. Okay, so now that we've got that, let's take a look at these two equations. Now, in the last example, we were given a nice, easy example because we already had a pair of variable terms that were opposites. Here, we're not so fortunate. I have negative 5x and I have negative x. Those aren't opposites. I have negative 6y and negative 6y. Those aren't opposites. But it's still kind of easy because if I wanted to, I could very easily make these two opposites. All I would need to do is multiply one of the equations by negative 1, and that negative 6y would become positive 6y. Remember, I can multiply both sides of an equation by the same non-zero number. I can just take this equation here, and I can multiply both sides by negative 1. And what I'd get is negative 1 times negative 5x is 5x. Negative 1 times negative 6y is 6y. Negative 1 times 13 is negative 13, so equals negative 13. And this equation stays the same. So we have negative x minus 6y equals negative 7. Now, let me drag this down here. What you can see is you have 6y and negative 6y. Those are now opposites. So when we sum the left sides and set that equal to the sum of the right sides, that variable is going to drop out. So let's go ahead and do that. So we want to add the left sides together, set this equal to the sum of the right sides. Now generally, we do this vertically. In the last example, I did it horizontally just to show you. So you just put a plus sign out here and a plus sign out here. So 5x minus x is 4x. 6y minus 6y is 0y, right? It's just eliminated. So you can line this out. And this is equal to negative 13 minus 7. This is negative 20. So I have 4x is equal to negative 20. Of course, to solve for x, I divide both sides by 4. And I get x is equal to negative 5. So at this point, again, I can erase everything. I just need my two original equations. All right, so we know x equals negative 5. We don't know the value for y yet. So I'm going to plug a negative 5 in for x, either in equation 1 or equation 2. It looks way easier to do it with equation 2, so let's do that. So we would have negative 7 plus a negative 5, and this equals negative 6y. Negative 7 plus negative 5 is negative 12, so you'd have negative 12 is equal to negative 6y. We would divide both sides of the equation by negative 6. This would cancel. You'd have y is equal to 2. So x is negative 5, y is 2. All right, let's erase everything. Let's go ahead and check. So we would have negative 5 times, plug in a negative 5 for x, minus 6 times, plug in a 2 for y, and this equals 13. So negative 5 times negative 5 is 25. Negative 6 times 2 is negative 12, and then this equals 13. We know 25 minus 12 is 13. You would get 13 equals 13 here, so it checks out here. All right, in the next one, equation number 2, we've got negative 7 plus, for x I've got negative 5, and this should be equal to negative 6 times 2. Negative 7 plus negative 5 is negative 12, and this equals negative 6 times 2 is negative 12 as well. So it works out here also. So this ordered pair negative 5 comma 2, or an x value of negative 5, a y value of 2, is our solution for the system. All right, for the next one, we're going to look at 2x minus 6y equals 0, and then negative 5x minus 3y equals negative 18. So again, I like to number my equations. This is going to be equation 1. This is going to be equation 2. Now, we want our equations to be in standard form. So ax plus by equals c. This one's in standard form, so is this one. So we're good to go there. Now, I want one pair of variable terms to be opposites. Don't have that. I have 2x and negative 5x. I have negative 6y, negative 3y. So looking at it, what's the easier option? Do I want to target my x variable or my y variable? Well, it looks like to me it's easier to target y. The coefficient of y here is negative 6. The coefficient here is negative 3. So what I can do is I can multiply equation 2 on both sides by negative 2. And what that's going to do is give me a value of positive 6 here. So if I have positive 6y here and negative 6y here, those are now opposites. So let's go ahead and crank that out. So for equation 2, I have negative 5x minus 3y equals negative 18. And I'm going to be multiplying both sides by negative 2. So negative 2 times negative 5x is 10x. Negative 2 times negative 3y is plus 6y. And this equals negative 18 times negative 2, which is 36. So now that that's done, let me write equation 1 on the top of this. So 2x minus 6y equals 0. So now we're at our step where we can add the left sides together, set this equal to the sum of the right sides. So we're going to add here, add here. So 2x plus 10x is 12x. Negative 6y plus 6y is 0y, or just 0. This will be eliminated. 0 plus 36 is 36. So you get 12x equals 36. Of course, you can divide both sides by 12, and you'll get x is equal to 3. So let's erase that. As an ordered pair, 3 will be the x value. Again, we don't know the y value yet. So I can plug a 3 in for x in equation 1 or 2. Doesn't matter. Let's just go ahead and plug it in for equation 2. So I'd have negative 5 times 3 minus 3y equals negative 18. I'm going to multiply negative 5 times 3, that's negative 15. Then minus 3y equals negative 18. If I add 15 to each side of the equation, that would cancel. I'll have negative 3y is equal to negative 18 plus 15 is going to give me negative 3. I would divide both sides of the equation by negative 3. This will cancel. I'll have y is equal to 1. So x is 3, y is 1. So let's go ahead and check this guy. So in the first equation, equation 1, we'd have 2 times my x value is 3, minus 6 times my y value is 1, and this should equal 0. Of course, this would be 2 times 3 or 6, minus 6 times 1, which is 6. 6 minus 6 is obviously 0. You would get 0 equals 0. So yeah, it works out here. In the second equation, equation 2, you would have negative 5 times x, again, x is 3, minus 3 times y is 1. This should equal negative 18. Negative 5 times 3 is negative 15. Negative 3 times 1 is negative 3. So negative 15 minus 3 should equal negative 18. And again, it does. You get negative 18 equals negative 18. So it works out here as well. So our solution here is the ordered pair 3, 1, where again, an x value of 3, a y value of 1. All right, let's take a look at another example. So we have negative 3 equals 3y plus 3x. We have 7/4 y equals x plus 15/4. So this is equation 1, and this is going to be my equation 2. If I want it to look like this, ax plus by equals c. So for my first equation, I could just simply write it as 3x plus 3y is equal to negative 3. So that solves that. For the second equation, I can subtract x away from each side. So let me write this over here. If I have 7/4 y is equal to x plus 15/4, I can subtract x away from each side of the equation. That'll cancel. So I can reorder this and just put negative x out in front plus 7/4 y is equal to 15/4. Now, it's not necessary to do this, but it's more convenient to work with equations that don't have fractions. So go ahead and do yourself a favor. Multiply both sides of this equation by 4 and get rid of those denominators. So 4 times negative x is negative 4x. 4 times 7/4 is 7. So this would be plus 7y. And this equals 4 times 15/4 is 15. So let's erase all of this, and we'll drag this up here. Okay, let me scroll down and get a little room going. Now what we see is we have 3x and negative 4x, 3y and 7y. But what would be easier to make into opposites? Well, both of them would be about the same amount of work. And what I can do is I'll just go with I'll target x. So to target x, we think about 3 and negative 4. The least common multiple between the two would be 12. So I want one to be positive 12 and one to be negative 12. Well, that's really easy to do. If I have 3x plus 3y equals -3, I can multiply both sides of this equation by +4. And what that is going to give me, 4 times 3x is 12x. 4 times 3y is plus 12y. This would be equal to 4 times -3, which is -12. Let's erase that. Then for this one, if I have -4x plus 7y equals 15, again, I want -12 here. So I would multiply both sides of this equation by 3. So 3 times -4x is -12x. 3 times 7y is 21y. And then 3 times 15 is 45. So now I have a pair of variable terms that are opposites. I have 12x and -12x. So we're basically good to go. We would add the left sides together. We'd set this equal to the sum of the right sides. So 12x minus 12x, that's 0x or just 0. 12y plus 21y would be 33y. And this equals -12 plus 45 is 33. So if I divide both sides of the equation by 33, I would get that y is equal to 1. All right, so our ordered pair would be something for x, comma, 1 for y. Now I can plug a 1 in for y in either equation 1 or 2. Looks like it's a whole lot easier to work with equation 1 because, again, I'll have to deal with those fractions. So let's go ahead and do -3. Okay, -3 is equal to 3 times y. Y is 1, so 3 times 1 plus 3x. So I'd have -3 is equal to, this will just be 3 plus 3x. Let's subtract 3 away from each side of the equation. That'll cancel. I'll have -6 is equal to 3x. Let's now divide both sides by 3. And what I'll have is x is equal to -2. So x here is -2, y is 1. All right, so let's go ahead and plug into each original equation. We have -3 is equal to 3 times y. Y is 1. Plus 3 times x. X is -2. So I'd have -3 is equal to, we know 3 times 1 is 3. 3 times -2 is -6. So if I had 3 plus -6, that would be -3. So you get -3 equals -3. So it works out here. For the next one, I have 7/4 times y. Y is 1. This equals x, which is -2, plus 15/4. So we know 7/4 times 1 is just 7/4. So just, you can erase that. For this one, I need a common denominator. So I would multiply this by 4 over 4. So I'd have -2 times 4, that's -8. -8 over 4. Now if I had -8 and 15, I get 7 over the common denominator of 4. So yeah, this is going to be 7/4 is equal to 7/4. So it works out here as well. So our ordered pair -2, 1, or an x value of -2, a y value of 1, is our solution for the system. All right, now we've already seen this in the substitution video. When the variables are eliminated, okay, all of them, there's nothing left in the equation you're working with. When the statement is true, there's infinitely many solutions. So if you get something like 15 equals 15, 29 equals 29, 35 equals 35, so on and so forth. If the statement is false, so 3 equals -2, 7 equals -21, so on and so forth, there's no solution, okay? So in this case right here, the second case, they are parallel lines, okay? So they are parallel lines. In this case, it's the same line. It's the same line. It's just algebraically manipulated to look different, okay? And the way you can tell for sure, for this type where there's an infinite number of solutions, just solve the equations for y, you can see you have the same equation. For this one, where there's no solution, solve the equations for y, you're going to see you have the same slope, but different y-intercepts, so you know you have parallel lines. Parallel lines don't intersect, so there's no possible solution. All right, let's take a look at some special case scenarios. So we have 14y plus 21x equals -14. You have -3x equals 5 plus 2y. So let's say this is equation 1, this is equation 2. So for equation 1, again, we want to put this in ax plus by equals c. or standard form. And so all I'm going to do is just switch the order. So I would write this as 21x plus 14y is equal to negative 14. For this one, if I have negative 3x is equal to 5 plus 2y, all I need to do is subtract 2y away from each side of the equation. So this would cancel. So I'd have negative 3x minus 2y equals 5. So let me kind of write that a little better. Negative 3x minus 2y is equal to 5. All right. So now I'm looking to make one pair of variable terms into opposites. And again, you can pick either one here. It's about the same amount of work. You have negative 3 and you have 21. So obviously, if I multiplied negative 3 by 7, I would get negative 21 there. So the coefficient here would be negative 21. The coefficient here would be positive 21. Equally as easy, if I multiply this guy here by positive 7, negative 2 times positive 7 would be negative 14. Negative 14 and positive 14 are opposites. So whatever you want to do. I'm just going to go with x because that's the first one. So if I multiply both sides of this equation by 7, then what I'd have is negative 21x minus 14y is equal to 35. So I can just erase this one, and I'll drag this up. And now we can add the left sides together, set that equal to the sum of the right sides. So plus, plus. Now, you can see right away 21x minus 21x is 0. 14y minus 14y is 0. So I would have 0 on the left, and this equals negative 14 plus 35 is going to give me 21. So, is this a nonsensical statement? 0 equals 21. Yes, it is. It's obviously not true. So this is the case where we have two parallel lines, so there's no solution. So there's going to be no solution. And if you want to prove this to yourself, go ahead and pause the video, solve each equation for y. You're going to find that you have the same slope and different y-intercepts in each case, right? So they're parallel lines. So we can also do this, and we can say they're parallel lines. All right, let's take a look at another example. So suppose we see 32x minus 8 equals 8y. Negative 30y equals negative 120x plus 30. So again, I want this in standard form. So ax plus by equals c. So for this guy, again, I'm going to label these equations, equation 1 and equation 2. For equation 1, if I have 32x minus 8 equals 8y, let me add 8 to each side of the equation. Let me subtract 8y from both sides of the equation. So that's going to give me 32x minus 8y is equal to positive 8. Then for equation 2, all I need to do is add 120x to each side of the equation. I will have 120x minus 30y is equal to 30. All right. So this one's a little more tedious, and I would just choose the smaller coefficients here. So I'm going to work with y. So if I have negative 30 and I have negative 8, forget about the signs for a second. Just pretend you have 8 and you have 30. What's the least common multiple there? Okay, what's the least common multiple? Well, 8 is what? It's 2 times 2 times 2. 30 is what? It's 6 times 5, or it's 2 times 3 times 5. So really it would be 2 times 2 times 2 times 3 times 5, or 8 times 15, which is 120. So if I think about 120, I want one of these to be negative 120y, the other to be positive 120y. So let me multiply both sides of this equation by a negative 15. And let me multiply both sides of this equation by a positive 4. So 4 times 120x is 480x. 4 times negative 30y is minus 120y. 4 times 30 is 120. For this guy, negative 15 times 32 is negative 480. Then, of course, times x. Negative 15 times negative 8 is positive 120, then times y. And this equals 8 times negative 15, which is negative 120. So if I want to add the two left sides here together, and I want to add the two right sides here together, 480x minus 480x is 0. Negative 120y plus 120y is 0. 120 minus 120 is 0. So what do I get? I get 0 equals 0, which is true. So the variables have dropped out, and I'm left with a true statement. So there's an infinite number of solutions, right? These two equations are basically the same. They've just been algebraically manipulated to look different. So there's an infinite number of solutions. And again, you can solve each equation for y. That'd be the easiest thing you can do. And if you solve each equation for y, you're going to see that you have the exact same equation in each case. And therefore, whatever works in equation 1 also works in equation 2 because it's the same equation. So there would be an infinite number of solutions for this system.